Yep. All right, so we were talking about charging neutral objects by something called induction, polarization, or conduction, right? So there's three different methods of charging objects or giving them a net charge. From we're going to assume that uncharged objects are insulators or just uncharged, and uncharged objects. And so if we wanted to give them a polarity, like a positive or negative charge, like for example with the pieces of paper, which are naturally neutral, if you will, positive, equal distribution of positive and negative, so the net charge is 0. And then if we wanted to induce a charge and then conduct electricity, then one typical method was to take an uncharged rod, a polystyrene rod that we had, and then rubbed it with some fur. We rubbed the electrons off of the fur onto the polystyrene rod. Those electrons are going to attract protons into this material. The protons are going to be here. Electrons are rejected. And so we have this rod of material that is all negative because the the electrons coming off of the fur onto the rod and attracts these protons in the material. So this net charge here is inducing a charge in the paper here. You can call that charge by induction because induction is not touching, and then conduction would involve touch. So induction is creating a charge, with no touch. Try to keep things as simple as possible in our review here, with no touch. And then conduction is you're creating a charge or facilitating the creation of a charge by touching. These objects are going to touch each other. So now when I bring the negative rod here at the region of these protons, then we're going to have conduction. So we can create charge by touch, or better example for the conduction is like when you have a balloon, and or even with the fur on the rod, that's conduction. So the balloon, you rub your head with the balloon and electrons come off of your hair onto the balloon. The balloon sticks onto the wall. If you've ever done that, try it. Have no wind or anything, but that's conduction, creating charge. So via or with touch. Polarization is like now we have induced these poles to come towards each other. So when we polarize something, okay, this was once all scatterbrain positives and negatives all over the place, right? Whatever over there, right? Just all over. Neutral. So when we polarize, okay, there's kind of like a quote separation. These is negative charges here are attracting these polarized, or these protons that come to this pole, this section. And so now we have, if it was large enough charge on each, we have conductivity, have a spark, like we would have a Van de Graaff generator. So, but with this low level induction here, polarization, or we just bring them to their respective sides, and so they're going to attract. So now we have the attract when we touch them. So now we have the negative rod coming in, and then a piece of paper, protons are here and stuff like that, and opposites attract and like poles repel. So let me make this a little bit larger. Okay, so we have this. Electrons don't like electrons, but they love protons, and so we got this, and the piece of paper was stuck onto the rod. There's a picture I'm looking at right in the textbook that shows a demonstration of that very thing. When we have a negatively charged cone that's going to be picking up pieces of paper. Pieces of paper are not metallic. Metals are natural conductors of electricity, some more than others. Like aluminum is not really a good conductor, whereas copper, nickel, or some other metals are. But typically metals are better conductors. So when you have pieces of paper attracting or being attracted to this negative rod, kind of interesting because they're not naturally conductive, but we have created that charge. We've created the charge through induction. The stream of water that gets bent, we have induced a positive charge at that part of the water stream that's now attracted to the negative rod that's being brought to it, and the water bends, the last water bender. So we have, three different ways that we can create a charge. Conduction, balloon on hair. Induction, without touch, bring it together, and we have a bending action with the water stream and the like. And then polarization, just kind of like, in the mechanism of induction, we have created polarity. We have a positive pole here and a negative pole. So we have polarization as a result. So it doesn't really talk about polarization in your text, but that's also a type of charge creation. So we just looked at those different examples as different methods of creating charge. And then now we're going to get into the full mechanisms or the physics of this attraction. How can we quantify it? Can we predict? Can we get some sort of result from these types of charges? And so our first foray into that was talking about Coulomb's law, which is a law of attraction or repulsion even. So the Coulomb electric force law is an attractive and a repulsive force. Attractive, opposites, and repulsive, like charges. But even if we have a repulsive charge, the magnitude of the repulsion from those charges will be the same as the attraction, provided that the distance for either case is the same. We just have a region of two poles repelling or opposite poles attracting through the same distance. And so that is our kind of first properties involved with the Coulomb force law. So that's conduction, that's induction, that's polarization, and polarization creating opposite or just creating poles, right? Hence the name. So we moved on to Coulomb's law, and that's basically the electric force law. We say F sub E equals K Q1 Q2. These are absolute value over R squared. And this is the electric force. So now we're quantifying all those types of attraction that we just saw into an equation form, which was developed by Charles Coulomb, I believe in the 1800s, 1700s, somewhere in there, and showed that the attractive or repulsive force between two poles, opposite poles, or like poles is given by this relationship, this famous Coulomb experiment. So this is the electric force. Again, the 8.99 times 10 to the 9th. Don't have to write the units. I just know them, seeing them forever. This is sometimes written as 9 times 10 to the 9th because it's basically 9. And Q1, Q2 are your charges. And we're looking at two charges. And then the units are coulombs. Or capital C. And then R is the radial distance between the charges. Much like the electric force law, the distance R is from the centers of mass. So now we're not looking at them in terms of their mass, looking at them as in terms of their charge. We have two two masses or two electrons or one electron, one proton, and we're looking at the, force or law of attraction between the radial centers or radial distances. So let's say this is Q1, this is Q2, this is R, and K is the electric force constant, never changes no matter the magnitude of these charges, distance, it's just constant. And then from that, you can find the electric force. So we have all of our numbers. Let's say that Q1, 3 microcoulombs, Q2, 5 microcoulombs. And we use the micro or the femto because a coulomb of charge is really like, it's a lot of electrons. It's a huge amount of charge that we typically don't deal with in an experiment case because the results will be disastrous. We deal with micro because it's not as dense as 1 coulomb of charge. I'll show you what
Everything will go so fast with like 1 coulomb, like 1 whole coulomb.
Yeah, there's a lot of electrons in a coulomb of charge. Like, I think the real reason behind that is that it's just too much electricity to deal with. And so we're trying to mimic what would actually happen in an experiment case. So that's why the coulombs are going to be mostly in nanocoulombs, micros, and femtos, as opposed to just, okay, here's 3 megacoulombs. Well, you don't want to deal with something like that. I mean, you can get an answer, but is that something you want to go in and experiment and test? No, you blow up the entire lab. So try to mimic the theory with the experiment. So 8.99 times 10 to the 9th. And then, I mean, you can do this yourself if you wish, and the micro is this. And then say radial distance is, I say 25 meters. And let's just get a little answer here on our made up problem. Again, this is a basic electric force. And then, since this is review, I'm just going to kind of do a little bit reintroduction and just leave it there and keep going. 499, the 9th. So on the numerator, we should have got 0.134, 0.135 if you want to round up, 25 squared, 625, and then 135. So did you get 2.16 times 10 to the minus 4? Yeah, I should have gotten that. You can verify yourself that is it. It's a very small amount of force. The distance is very large. You got these very small charges 25 meters apart. I mean, intuitively, you should think, it's not going to be much force. And I'm implying that these are both positives. They're going to repel, but force is very small. They're going to drift away. Very, very slowly. That force is very small. Okay, so there's a bit on that. And the Coulomb experiment, you can see in the text, or you can go look it up. You guys don't have the text. So a bit on, I'm gonna change the view. So you can kind of see things as I continue writing. So we saw last time when we were here, like the K is also written as 1/4 pi epsilon naught, which is equal to kind of like your Gaussian units. And again, yeah, so those are all equal, where epsilon naught is called the permittivity of free space. It's basically the amount of space that the electric field would go through. How much is permitted? And that's 8.85 times 10 to the minus 12. And the units are the opposite, really. Coulomb squared, Newton meter squared. But you don't have to worry about the units. The numbers are there. Charge of an electron, same as a proton, 1.602 times 10 to the minus 19 coulombs. And that's typically negative. You designate an electron as negative charge. And like I said, the proton is the same magnitude, it's positive. Then let's talk about electron mass, or M sub E. 9.11 times 10 to the minus 31st kilograms. Mass of proton, 1.67 times 10 to the minus 27 kilograms. Like 1,000 times, or that would be like 10,000 times heavier than the electron, 10 to the fourth. And then the neutron is same mass as a proton. It's neutral, hence neutron, and 1.67. It's a little bit heavier, actually. These 6 fixed precision units, 1.67. So let's see. Okay. So yeah. So let me amend that. So they're not the same mass, like, not the same mass exactly. Almost. So let's see. See, a proton would be, let's see, 1.672, and see, a neutron would be 1.674. A little bit heavier than proton times 10 to the minus 27 kilograms. But since the neutron is neutral, we just typically deal with protons, electrons, because we're dealing with charges. Either you're the same charge or opposite charge. Going back to the electric force equation, we do absolute values because we don't want to confuse the sign of the charge with the sign of the force. But here's another way to talk about the Coulomb's law, K, Q1, Q2, R squared. Well, this, and if you wrote this in terms of like the R12 hat, so basically, let's say we have 2 protons, right, or 2 positive charges, right? And then this was, going to be charge 1, and it's charge 2. So the force of 1 on 2, or force of 1 on the force that 1 exerts on 2 would be this direction over this this direction, denoted by this variable here, this unit vector R12. So this is over the R12 direction, because this is the distance from 1 to 2, and this is the force of 1 on 2. So that's what this basically means. This is the force, the magnitude, and the direction. And you can write that as positive, whatever this is, or write it as the unit vector notation. So, and the same thing obviously applies if they were opposite charges. This is positive and positive. They repel. This is the force of 2 on 1. It's negative because it goes left. And then let's say if we had the positive and this is negative, then the force of 1 on 2 would be like this, still over R12. It's just attractive. This is repulsive. That's all that is. Same expression. So again, if we wanted to find the total force in a configuration of charges, it doesn't have to be 2, it can be 100 or whatever. Then the total force in the system let's say that we want to find the total force, and we had like 4 charges. We want to find the total force on the first charge, or the charge that we call 1. Then it would just be the sum of the forces of the second charge on 1, the third charge on 1, a fourth charge on 1. So we add all those up as a vector and we get a net force. Or it's the same thing as saying that we've been familiar with. Net force is just the sum of all of the parts. I'm not worried about it being 0 or MA, but right now we're just saying that if you want to get the total or net force, it's going to be sum of all the individual guys. This right here says the total force on 1 is made up of 2 on 1, 3 on 1, 4 on 1. Let's say 1's here, 2, 3, 4, their distances. So let's say that all these were negative, this was positive. Okay, we got something that looks like that. 1, 2, 3, 4. This would be, in terms of that unit vector stuff, R12. Well, in terms of 2 on 1, so it'd be 2 on 1 because we're not going this way. We're going this way. So this would be 2, 1, 3, 1, 4, 1. So it's consistent with everything. So yeah, we for the rest of the audience out there, we're gonna skip past some example problems for the moment. We'll come to example problems when we get to new material. We may have a sample question on this, time permitting. What I was going to do next is go and talk about the electric field. So 23.4, this textbook, the electric field. Try to have a conversation over this. So the electric field is just basically the region of space through which the electric force acts. It's kind of like the medium. A gravitational field is the space or the region through which the force of gravity acts. And so the electric field does the same thing for electric force. Thing with the electric field is that you only need 1 charge to set up a field anywhere in space. You can find the electric field at any point. So common experiment, or one way to show this, is that if we had a large charge, call it Q, whatever, and then we had a test charge, call it Q naught, we can define the electric field in the same direction as this force. The field is the region of space between these 2 charges through which a force acts. And this Q naught is our test. So not only is the electric force going to be repulsive and point this way from Q on Q naught, the electric field points in the same direction. The electric field is that medium for this repulsive force to take place. So experimentally determined, the electric field is defined as the force between these 2 charges, or the force of this charge on this test charge, force divided by Q naught, because only in this configuration are we looking at the electric field and force on Q naught. Well, I'm going to take a step further. We know that the electric force is K Q over Q naught over R squared over Q naught. That goes away. And so we're left with KQ over R squared. So by the equation here, the math shows that we only need 1 charge to set up a E field. I can find that field anywhere. So I have a random charge here. And the electric field, we're going to summarize some other points about it. It's perpendicular from the charge, goes to any point in space. Let's assume that's perpendicular. I can find electric fields at all of these places from this central charge here. P, Q, R, whatever the points are. And then when we do try to find the electric field at those points, we can treat those points like positive charges. As if a test charge is going to be there, the field at that point exists. It will be there whether the test charge was there or not, just like we have here. And so kind of treat those points in space as positive charges. It doesn't say proton, but it didn't have to be the charge of proton. It could be any positive charge. So the electric field conventionally emanates from positive charges. It goes out like this. And then for negative charges, they terminate or end on negative charges. So, okay. So this is a negative charge right there. So the electric field goes inward on the negatives, outward from positive. So again, definition of electric field in our review schema. And if there's any questions, fire away. For you guys' review and the other audience, I'm just trying to make this as conversational, easy as possible. But yeah, just get to some examples in time. So inward on negative charges. Electric field, only need one charge. Electric force, 2 or more. We do 2 at a time. So electric field, like the electric force, is a vector. Experimentally, F over Q naught. So, so the electric field is a vector. It's a result of a vector over a scalar to produce a new vector. And then if we wanted to find the equation for electric field from this configuration, Q naught times E, the same thing as K, Q naught Q over R squared. If our two charges, the test charge Q naught and big Q. So those are equal. Force measured in newtons, any force. The electric field is in newtons per coulomb, because charge is in coulombs, force is in newtons. All right, here's the fun part, right? We had the electric field of a continuous charge distribution. Now we're going from points to arbitrary shapes, just like we do anytime in physics. The baseline is particles, points. Do we understand that? Now let's blow it up to an actual shape. Pear shapes, spherical shapes, circular, linear, all that good stuff. Okay. So 23.5. Electric field of a continuous charge distribution. Basically, the electric field from an extended object, which is the sum of many point charges. We go from one to like 2 point charges to a sum of many. And just so I don't be too dogmatic on this bit, when we have an extended object that consists of many point charges, we sum them up to get the electric field from that entire shape. We are doing an integral. We are integrating over all of those charges to get an electric field. So our basic electric field equation, KQ over R squared, this will be a point. But when we have many points, basically, this becomes the sum of all of the Q's. This is Qi, or I denotes each particle. So I goes from 1 to 2 to however many particles make up this shape. Q1, Q2, whatever. So these are all little pieces of the entire Q. And when we sum them up, we get a large Q. But we just can't get big Q out of here because this is not a, a point mass. Also, it's not point mass as we had it. So it's a point mass based on the geometry of the shape. So it's a continuous charge distribution, but what kind of distribution is it? The dq over an area or two-dimensional is different than three-dimensional, and also one-dimensional, which is a line. So we have to define different dqs for our different shapes. Basic idea. So now, if we have a volume, let's say a sphere, we have a volume charge density. They all look like your typical, density equation, mass over volume. So we're not dealing with masses, although charges have mass. We're dealing with their charge. So this would be Q over V. That's the volume charge density for a shape that has 3 dimensions, or it's 3-dimensional, like a ball or a sphere or something. Obviously, the units will be coulombs per cubic meter. And then we have, what you call a surface, I typically call it area charge density, or surface charge density, which would be denoted by sigma, which is Q over A. And then we have a linear charge density, which is denoted by lambda, which is Q over L. So depending on what type of shape it is, we can get our different dqs. We have to integrate in terms of the type of charge density that's there. Is it volume? Is it surface? Is it linear? And so at this point, I think it's good to do a example over this charge density stuff. And then we'll push forward, as it were, to our next chapter and all that good stuff. So today is, let's see if we can get, hopefully we can get to the end of 24. And then Tuesday we get to 25. That's where we left off last time. So I'm looking at this textbook, I'll just call it what it is, example 23.6. And we're trying to find the electric field due to a charged rod. You guys out there have seen this, it's in your notes. So even if it was unclear before, now we can go over it again and hopefully get that. So the picture, we have a point P here, and we have this rod. So again, we're no longer looking at point charges. We're looking at charges based on the geometry of the shape. This is basically a line, rod, linear. each one of these parts is going to have their own little charge. So this dx, in terms of integration, will be related to its dq, because we know that lambda is dq over dl, the entire length, q over l. But at this point, we're not looking at the entire L, we're looking at a piece of L. So it's going to be dq is lambda dx. If this was q, then this would be lambda times L, because we now have summed up all the pieces. Each piece has its own little charge contribution. Let me finish drawing the picture. So this is our linear distance x. Kind of give a visual on what the dx is about, or the reason for that part of the picture. And then the length of the rod would come down here, because essentially we want to get the entire rod, how it throws out an electric field to point P, which is here. And point P, remember, it's like a proton. So this is positive and this is, quote, positive. And so the electric field would be to the left, as if it were repelling another positive charge. Okay, and then this little gap in between here is, we just call it A. Let's call it any variable, because we have the length of the rod plus the A distance to get to P. So everything's continuous, which helps us thinking about the problem. So now we can set up the equation to integrate all the pieces, and then as we do so, we will have found the electric field from this rod to that point P. We know if it was just a point charge, take Q over R squared. It was all these little guys. We saw that at the board. So this becomes the dE, because each one of these guys is given on its own E. E here, E here, E here, E here. K dQ over R squared. And we already know that dQ is lambda dx. And okay, well, R squared, okay, well, be careful about that. This R is going to go along the x-axis. Why do we choose that? I mean, because visually, we're going along the x-axis, the y-axis, or z-axis, any other axis, we call it radial distance R. If this was three-dimensional, not only would our charge density variable change, but then we change the variables to R. So we're talking about a rho in that case, a volume charge density that involves all three axes. Excuse me, lambda dx. So instead of R squared, we call this x squared. Because when it comes down to integration on the math level, we're going to have to integrate everything with respect to x. So if it was no distance here, or nothing else that could be in terms of x, we just integrate dx and it becomes x. That's the easiest integral. But this r becomes x squared, goes along the x-axis. And so now, when we integrate dE over here, okay, 1 second. Mouse is getting wacky. All right, hold on 1 second. All right, let's see if this works. okay, so when we integrate, we're going to integrate everything that can change. And so in this case, the only variable here that changes is the x, the dx. So everything else comes out of the integral. Let me just put the integral up for right now. And so, okay, I'll do this. Because right now what I'm writing is kind of like an indefinite integral, but we have definite bounds, so I'll be putting those in a second. So, all right, so we got this, okay. This guy, you just integrate over dE, it becomes all E. And then these two guys are constant. Okay, they come out of the integrand, and the boundaries are going to be from A to L plus A. Now you might think, just put myself in a mind of a student or whatever, right? You might think it's L plus A to A because it's going over here. This is the point over here, right? Well, the bounds are from the lowest to the highest. So we go from little a to L plus that. So that's why we write it like that. So then we got the dx for x squared. Okay, so we integrate that. So now when we integrate, we're integrating. So dx is basically telling us, okay, so just plain English, we want to sum all of the x pieces wherever x occurs. And that's kind of what's happening here. I want to get the result of this for all the dx's. What does this equal? When I sum all the dx's, what happens? What happens? So the basic idea of integration is we'll take a variable, like call it x in this case, and we look at its exponent. And what we do for the integration is we do what's called the antiderivative. We're going to get the function whose derivative would give us what we have in the beginning here. So we're going backwards, going to the function, whatever function that will be. Once I take the derivative of that, I will get the original function that I see here, this 1 over x squared business. So I'm anti-deriving. Because if I derived, I'll take the function that I need and go to 1 over x squared. So it's backwards. I'm going anti, the other way. So antiderivative, x to the n plus 1 over n plus 1. Just leave the little math aside, but necessary to get the result here, antiderivative. So I can write this 1 over x squared as x to the minus 2 power. And do this, it becomes easier. So then x to the minus 2 plus 1, do the same thing on the bottom, negative 2 plus 1, where n represents the exponent. The exponent is 2. Minus 2, right? Minus 2 plus 1, and that becomes negative 1 over x. So the antiderivative, this integral becomes negative 1 over x. Negative 1 over x. If I take the derivative of this, it becomes x to the minus 2. Or 1 over x to the minus 2. So basically, when I do this, take the derivative of this function, which is, subtracting 1 to both sides, or subtracting 1 top and bottom here. This is negative. This is this is x to the minus 2, because I have a minus 2 and a minus up there. Oh, no. My fault. I'm doing an antiderivative again. So it'd be negative x to the minus 1. And then I subtract minus 1 here. And then I do the same thing. Then I multiply this by minus 1 and then subtract. Get my operations all backwards. So this is negative, this is x to the minus 2, this is positive, so this becomes positive x to the minus 2, which is 1 over x squared, which is what we have right there. So that's antiderivative. Then we derive the antiderivative function, which is negative 1 over x, and we get the original function back that we're trying to take the antiderivative over the integral of. So it's just backwardsly there. So okay, so hopefully you people out there, you get to this point. I make a disclaimer on this video. Know your basic calculus. Okay, but that's yeah, how we get it. So back to the deal. It's a k lambda, and our solution is negative 1 over x. It's a l plus a, and so now it becomes easy to. So now what we got to do is to substitute the final piece minus the initial piece, which we did way back in displacements and stuff. So we go negative 1 over L plus A minus 1 over A. I'll cut out the middleman and just write the final result. It'll be K lambda over okay, I'm going to re-express this in terms of the charge density. Why? Because electric field commonly written in terms of the charge, right? So anyway, get to this point, lambda Q over L. So like, okay, cut out the middleman. I get the K Q over A L plus A. And this is my electric field from a linear charge distribution, a rod that has all this Q on it, throwing out an electric field to a point P. So that's just one example in that. I'm gonna push on ahead. That's why I need to do one example of that. All right, next topic is about electric field lines, but I'll just tell you one thing about it just to save a little time on that. Your electric field lines must be perpendicular. In electrostatics, only in electrostatics does your electric field lines, we deal with electric field lines that are perpendicular from the charge. And electric field lines, they begin on positive charges and end on negative charges. We saw that already. Perpendicular to the charge. Begin from positive, end on negative. The number of electric field lines, one thing I didn't tell you guys in the first we'll go around, the number of electric field lines depend on the charge of the particle. So if you have 2Q here, and then this guy is like negative Q, there's going to be twice the number of electric field lines coming from 2Q and ending on negative Q. All right, so if I have 8 from here, 4 are going to land here. All right. No two field lines cross, so everything's perpendicular. Okay, let me amend that statement. Going back to the principle. The number of electric field lines, yes, are proportional to the magnitude of the charge. So if I have 8, so if I have 2Q here and this is negative Q, I'll have twice as many electric field lines coming off of 2Q than ending on negative Q. So yeah. Sorry, that was right the first time. All right, anyway, so I got, let's say I have 8. So 4 have ended, but the other 4 are just kind of wild and getting out there. So let's assume that these are perpendicular. I know they wrap around, but they're perpendicular from the charges. You guys understand that? See what I mean by that?
Yep.
Edward, you following? So the number of field lines relate to the amount of charge. So if I have 8 from 2Q, 4 are going to end on negative Q. That makes sense? Edward, you there?
Yes, I'm here.
Okay.
I just
Yeah,
thumbs up.
probably mute. Did you understand that?
Yeah, kind
What don't you understand? Say yes or no. No kind of.
of. Yeah, you know, everything that we learn here, like during class. After class, like I kind of analyze it and kind of review it. And
But I'm not asking you that. I'm asking, do you understand what I just said there? Do
oh
you
yeah,
understand that? Okay, if I have 8 field lines coming off of 2Q and 4 end on Q, does that make sense?
the one with the negative Q.
Yeah, do you understand this picture?
Yes, yes.
Oh, okay, that's why I wanted to make sure before we go on. So yeah, I mean, that's kind of like the nuts and bolts of 23 and 24. What did I tell you guys about 24? Gauss's law. It's like, okay, all right, so you have your electric fields and electric forces. What Gauss's law does, it says, how much electric field can I get in a certain region of space? Because all I need is one charge to make an electric field. Gauss's law just restricts you to a certain kind of space through which the electric field goes through. Is that space spherical? Is it 3-dimensional? Is it 2-dimensional? And we can be linear as well. You can have a Gaussian surface around a linear charge. So basically, let's just talk about that. That's just kind of the conversation. Okay, what is Gauss's law? What is that all about? Okay, well, it's an electric field through some space, through some defined space, through a Gaussian surface. The way Gauss thought about it, and you can test it out. I mean, it's really, Gaussian spaces are not real. They're just kind of arbitrary ways of studying electric fields in a certain space. Does it exist? Does it not exist? Okay. Let me pause here a second. Okay, so chapter 24, Gauss's law, electric flux. We shall start off with the concept of electric flux. So electric flux is basically how much electric field goes through a certain region of space. Because the plural of flow is flux. You don't say flows unless you're a rapper. He's got mad flows. flows, but you know, technically the plural of flow is flux. Okay. You guys know about rap artists out there. Electric field lines moving through an area A. So we talked about cross-sectional area. Ooh, I just pushed the darn button on the pen. Okay, whose plane is perpendicular to the field? All right, that's a bunch of words. What does that look like? Let's say we have a sheet of paper and we're looking at it from the side. We have electric field going through like this. This electric field is perpendicular to this plane, forms 90 degrees, but I guess I'll get to that in a moment. Okay. The thought is there. This electric field is going to be parallel to the normal vector. So we're going to define this normal vector as just basically the pointer, basically the direction of the electric field. So we call this n hat. It's not necessarily like a normal force. It's just a pointer. It's a unit pointer for the electric field. It says that basically the electric field is parallel to this arbitrary normal vector. Same direction as the normal plane, the vector perpendicular to the plane of the paper. Here's paper. Okay, so electric flux is electric field times the area. Units, Newton meters squared per Coulomb. So going forward on that. All right. So this flux is a number of electric field lines crossing this area that we see here, you know, that we see there. And the angle between this normal pointing vector and each electric field line is going to be 0. That basically means that the electric field is parallel to the normal vector, perpendicular to the plane. But for flux to even happen, we have to have the electric field go through that area, and that each electric field line is going to be parallel to this pointer. And that means that the angle between both E and N hat, the pointer, is 0 degrees. So let's say that the sheet of paper was not perpendicular. It's like this, and electric field line is still going like flowing through, like so. Field lines here. Then the normal pointer would be obviously always perpendicular to the plane of the paper, something like this. So in that case, we'd be looking at the part of this normal vector. It's basically, so this plane of the paper has area A, total area A, and so each little piece here is dA. Each dA through which this electric field goes through is in the direction of the normal vector, like here. So this normal vector is basically trying to say this as I'm imagining it. The normal vector there is the same direction as if a part of this area was moving with E. So it's a little dA going along with it. But obviously that's not happening, but This is another way to think about what's happening here. So the dA is moving in the same direction as E. We define electric flux as E times A. In this case, it's not perpendicular. The electric field is not perpendicular to the plane. So we have to find the part of N that is parallel to E, because by definition, this E and this N vector must be parallel to each other, angle of 0. So the part of N that is perpendicular or parallel to E is the cosine component. So we say E and N hat cosine theta. By definition, electric flux is E times A. So we don't say E times N hat cosine theta for the electric flux. We're looking at the part, the piece of this area that's moving in that same direction as N hat, which is dA. So we say, in this case, say d phi E equals E dot dA. Cosine theta, rather. So that's a general equation. So then when we integrate this, we get the total flux is going to be EA cosine theta. I wanted to kind of, at least for the moment, not get too bogged down into mathematical semantics of this whole thing. It's just that seeing the solution here, we can think about this normal vector as the direction of each dA as if it was flowing with the E to make the angle 0. But in this case, it's not perpendicular to the sheet. So we have to, N is always going to be perpendicular. It's normal. Normal means perpendicular, mathematic in math. But we're looking at the part of the dA that moves with it, and that's the dA cosine theta. And when we integrate that, we get this. So that's the electric flux. Okay. Blah, 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 blah. I'm not going to bog down into that. Let's get into Gauss's law. In order to appreciate Gauss's law, we have to appreciate what flux is. Flux is something moving through some kind of surface. And we're going to see in Gauss's law different Gaussian surfaces. Gauss's law, apostrophe S. Okay, so Gauss's law deals with, okay, we have a net electric flux through a closed surface which we call some arbitrary Gaussian surface. Gaussian surfaces, you can't just look outside and, oh, there's a Gaussian surface. It's something to kind of confine the problem, right? Net electric flux through a closed surface, which is a Gaussian surface, and the charge enclosed. Okay, when we have this, when we have a flux through a closed surface, and there's an electric charge within that surface, we have Gauss's law. So all Gauss's law is, okay, I take a charge, it's throwing out electric fields in space, define a surface around it, and I can get the amount of electric field through that surface. I can find out what the flux is through that surface. I can, determine the area of the surface. I mean, you have to have some kind of surface for flux. That's why flux is important to understand. Okay, so net electric flux through a closed surface, a Gaussian surface, and the charge enclosed within that surface, basically Gauss's law. Okay. So, all right. So we know that this is the case, E times A. But then when we, if we had, we were looking at each part of the area through which the E flows through, and we're not going to say DE because we're going to assume that E is continuous, it's uniform. There's no pieces of E. So E is going through each DA. Well, when we integrate, we get something like this. We integrate the left side first, and then we have, okay, so we'll do E dot dA, which becomes just EA. So the difference between this integral here versus this one, this would be more or less of a line integral. This would be a surface integral. So if E was actually changing, we could go to something called a double integral and figure out what's happening there. And then, you know, especially in multivariable calculus, we go to the triple integrals when we're dealing with 3 variables, especially when we're dealing with spheres where everything is changing. We have the radius, we have both types of angles changing, the rotating angle and precessional angle changing. I'm going off on a tangent, I know. But yeah, there's different types of integrals that do exist, and you'll see as you go along. The line integral, surface integral, this little circle here, this basically means that I got all my E field going through this surface. That's why it's a surface integral. I'm no longer just going through a line, I'm going through some Gaussian surface. All right. So now, let's say that our Gaussian surface was spherical. We know that the area of a sphere, well, not the area of a sphere, the surface area of a sphere, surface integral, the surface area of a sphere would be 4 pi r squared. So let's say we have a charge moving through a Gaussian spherical surface. And we'll take this integral here. E is constant, so we can take it out of the integral. We are going to integrate over the surface area. Surface area of a sphere, integrate all the pieces, we get 4 pi r squared. So that's phi E. That's the electric flux. Now, we also know electric field is kq over r squared. So, move forward over here. We have phi E k q over r squared 4 pi r squared, because this was E, this is A.
So does this eventually end up in Q over epsilon naught eventually?
Yep.
Yep.
Totally. So get rid of that, and this is going to be k q times 4 pi. And good thinking, good looking ahead, because we know that k is equal to 1 over 4 pi epsilon naught. And that becomes q 4 pi over 4 pi epsilon naught, bam, bam, and you're right on it. The electric flux for a point charge is q over epsilon naught through some surface, some Gaussian surface. Now, obviously, if we're enclosing all of the charge q, that's going to move through this whatever Gaussian surface it is. We've seen that as an example last time. If we're trying to find the electric field through a Gaussian surface within the charge, let's say this charge is huge or whatever, and we define a Gaussian surface within the charge itself. Now we can't just take Q, we have to take the volume density, charge density of that spherical charge, let's say, or if it's a sheet of paper or if it's a line. We have to look at it in terms of little q's, dq's in that case, as opposed to the whole q. Because now when we're on the interior of the charge, we're looking at a part of the charge that makes up the whole charge. So that's why we have to go to different densities, charge densities, whether it's volume, surface, or linear. But this will work for a complete charge, Q. And it's, you know, typically written as N for enclosed. So I have a charge here and I define a Gaussian surface around it. I can find the electric flux through it. This is enclosed or inside or whatever. I can do this. This is arbitrary Gaussian surface around a sphere. And if this is a rod, I can make another Gaussian surface around that and then do it in terms of the linear charge density. Or surface charge density, you know, depending on what type of surface I'm surrounding it by. Yeah, so the surfaces are arbitrary, but depending on what surface we choose, we'll have to conform to that charge density. Okay, so I think yeah, we have a little bit of time to do one example here. All right, little dead air here. Let me just get to my examples. Okay, so this is our chapter 24 in our book. So we're going to go on to our example 24.3. And we have a spherically symmetric charge distribution. An insulating solid sphere of radius A has a uniform volume charge density rho and carries a total positive charge Q. Calculate the magnitude of the electric field at a point outside of the sphere. So outside of the sphere, we're going to have this electric field go through up to this radius of this Gaussian surface. So we have this charge Q here, and it has a radius A, and we enclose it by a spherical Gaussian surface, and we want to find the electric field at point R. Now, we're dealing with electric flux, which is Q over epsilon naught. So we have to define a surface by which this field goes through for the flux definition to hold true. That's just our context. Because otherwise you might say, oh, I just find the electric field at that point. Well, we're dealing with flux, which is directly related to field, not just dealing with electric field though, by itself. Okay. So we have electric flux, which is E dot dA. And we know that that's equal to Q over epsilon naught. We want to find the field. This is the easiest case because we're surrounding the entire charge Q with this Gaussian surface, so we don't have to break up Q into any type of density. So we know that those are always, so when we integrate this, this becomes EA equals Q over epsilon naught. And they want you to find the electric field through this Gaussian surface at this point. So another way to kind of think this is not just electric field. So even though this is a Gaussian surface, we're looking at it two-dimensionally, it is actually three-dimensional. And so therefore, it's going through all points of that surface to distance r. Or maybe that's not easily visualized. Keep it two-dimensional, going a distance r to this point through this spherical surface. So E, oh, and surface area, surface of, area of a surface area of the sphere is 4 pi r squared. So we have Q over A epsilon naught, which is Q over 4 pi r squared epsilon naught. And we know that K is 1 over 4 pi epsilon naught. So this just becomes K Q over R squared. Yay. Yay, the original electric field equation, right? Perhaps this is the best way to take this. This Gaussian surface can start any arbitrary distance from the charge. And if I say, for instance, right at the surface, going all just right here, and then it says, what is the electric field at R? So I'm now taking that surface and extending it. So it's flowing through that surface that, let's say I started here and I'm just blowing it up. So I'm going, my Gaussian surface is actually larger, than if I started at the charge itself. So I'm coming out to R as opposed to right at the surface. So there is, oops, there's that. So now they want you to find the magnitude of the electric field at a point inside the sphere. So inside the sphere, it's not just Q, it's dQ. And so we have to figure out what kind of dQ. Well, it's a sphere, it's volume charge density. So now I have to integrate, if I needed to integrate, but I have to now represent Q in terms of the volume charge density. So I have my charge, and now my Gaussian surface is inside. Little r here, and this is my full extent of my A. So this is all about your dQ. Electric flux is enclosed charge, enclosed in a Gaussian surface over epsilon naught. Well, Q enclosed in this case is going to be equal to density times volume, because volume charge density is Q over V, and Q will just be density times volume. Then volume of a sphere. Okay, I'll just continue right in before I get over there. That'll be rho times 4/3 pi r cubed, right? Therefore, EA, it's in the game. QN over epsilon naught. We know the surface area of a sphere, 4 pi r squared, equals rho times volume. Remember, because that's Q, 4/3 over epsilon naught. These guys go away. This guy goes away. Well, this is one's left over because he's cubed. Sorry about that. So r squared, and there's just one r left. And we have, okay, E is rho times R epsilon naught. If you left that like on a test or something for me or whatever, should be all right. But generally speaking, electric field is in terms of the charge. So let's see if we can represent rho. Let's get it simplified even further. So we're going to substitute rho as Q over the volume. And we're not going to use R, the Gaussian R. We're going to use the radius of the charge because we want to get how each dq sums up to the extent of the charge. And the extent of the charge ends at radius A. So we'll have Q over 4/3, not pi R cubed, but pi A cubed. Epsilon, K is 1 over 4 pi epsilon naught. For E, and we're just going to simplify that, equals rho times R, right? So it's like a kind of a kludgy or I want to say hokey way of integrating all the way up to A. But just it's more intuitive than anything. A cubed times R. And then we have, so 3 over epsilon naught. And so we know that epsilon naught, I say K is that. So epsilon naught will be 1 over 4 pi K. So then we have 3 over 4 pi K. Because epsilon naught is this, 1 over epsilon naught, maybe we just divide it again. And you do all your stuff here. You know, crossing everything out. And so we're left with, in terms of the Q, this Ke can be flipped up, or this Coulomb constant. It becomes KQ over A cubed times R. Yeah, I'm just assuming that we're pretty sound algebraically. Like I said, disclaimer, your basic calculus. Anybody can follow along. You want to just be tough-minded about it. So that's just our example of finding electric flux at a particular point using Gaussian surfaces, using a Gaussian surface that encloses the entire charge or within the charge. Any questions on that? So let's talk a little bit about a what if scenario. You know, we're gonna see if what happens. Suppose in this scenario, suppose that the radial position R equals A is approached from inside the sphere and from outside. So we're looking at the sphere and we're looking at how the electric field is going to look like at A from the inside and the outside. So we're going to approach, there's going to be these bounds that approach like this. How does the electric field look like? What does it look like? What's going on with it? Do we obtain the same value of the electric field from both directions? Okay, so first case would be, let's take a look from the outside. So we got the electric field already. So we're basically going to take this electric field, go all the way to A, or radius A. We're going to be approaching this distance R from wherever R is to A from the outside. So we're going to look at basically a limit as R goes to A from the outside, and we have our electric field from the outside, which we defined as KQ over R squared. Now R is equal to A. It approximates to A. It's not exactly equal to A, it's approaching A. So we can just make a substitution as if it was A, and then we'll say KQ over A squared. That's basically saying that's what the electric field would look like if you approached it from the outside of the sphere. And this case. Okay, and then how about from the inside? So we're going from this point all the way to the edge from the inside. So the electric field would have the same limit as R goes to A from the inside. And so basically, okay, our limiting case is the same, but what changes is the fact that our electric field is different from both sides. From the inside, it's what we derived before, and then from the outside is this. When we have the Gaussian surface, it'll close the whole thing, and the Gaussian surface on the inside is what, we've got that KQ over A cubed times R business. So, and then we just take the limit as this is our condition for the limit, KQ over A cubed times R. Well, R approaches A. So we're no longer looking at R itself. We were looking at it as if it was going to be A from the inside. So that's what I was talking about before. We take the Gaussian surface and just blow it up to the extreme, which is R equals A. And this is basically the, what do you call it? The exact or rigorous way to do that. So this becomes KQ over A cubed times A, and that becomes KQ over A squared. What do you notice, guys, about both cases?
Has the radius squared on it.
What do you notice about the electric field for both cases? You're right, the radius squared. Is the electric field the same?
I think electric field is different from the on the surface and inside,
What does this say?
Okay, they're quite the same, whether or not the radius approaches from outside or inside.
Yeah, they're the same value, no matter how you approach it. And so the electric field's the same. And this kind of goes into later on down the line when we get to electrodynamics, is something kind of like the, if I remember right, the method of images, where you can start looking at different either different types of electric field or different limiting cases, and see how the electric field changes, based on the surfaces, the geometry, more or less certain limiting cases. But in this case, situation, our electric field is the same. It doesn't matter. Even though this is our value from the inside, at this point, it's the same. Yeah. So this is different ways of treating and looking at this scenario. So good. We're making some good headway in our review, and we're getting up to our climactic events of beginning of chapter 25. So graphically, let's see. We were looking at both cases. So we have electric field versus radius. So as we come from the center of the charge, like there's no E field at basically nothing at the center, right? And then our electric field goes from nothing to a particular, like to a maximum value within on the inside of the center, E max on the inside, if you will. So we're gonna, it's gonna steadily increase until we reach radius A, and then that's on the inside, and then from the outside, as the electric field radiates into all of space, it's going to drop off as 1 over r squared. K q over r squared. This is basically a 1 over r squared function. And that's linear. But this graph, I mean, just to kind of make some sense out of it, it's growing proportionate to the radius r. Again, wait a minute, we got r squared. It's not a line. Well, let's look at what happens. Oh, we found the electric field on the inside to be k q over a cubed times r. So if we make a graph of E versus R, this is linear. Hence we get this. And then this R, we know it's R, little r, big R. This is r squared, 1 over r squared. So that's why it does that. Any questions? You see why that is? We see that this is linear versus 1 over r squared. So last, talk about for conductors in electrostatic equilibrium. Basically, what conditions must be met in order to have a conductor in electrostatic equilibrium? Basically, the charges don't move. Well, in order for that to happen, the little charges that make up the big charge, nothing moves. It's static. The electric field is 0 everywhere inside the conductor. So we have a conductor, we have the surface here. There's nothing on the inside here. We can have an electric potential, but that's coming later. That concept's coming later. So, but the electric field is null on the inside. Charge is on the surface. Since the charge is on the surface, the electric field just outside of the surface is sigma over epsilon naught, because we know that flux is A, and then this will be Q over epsilon naught for electric flux. And then we know if we're talking about surface area, then we're looking at, well, no matter the surface could be spherical or circular. So surface area, so Q over A epsilon naught, and Q over A is sigma. That's why we get that. And then lastly, for electrostatic equilibrium, let's say we have an oddly shaped object look like this. The charge is the densest at small spaces. A regularly shaped conductor, the surface charge density is highest at small r. So this is, this little space, if we just, think about it in terms of a circle, it's small r versus big R here. And density is smaller, the larger radius. So those are your conditions of electrostatic equilibrium. We then went on to talk about an example of a sphere inside a spherical shell, different different values of the electric field based on where you are. I think for the moment I will just skip over that. As we have, reached the end of 24, I want to talk a little bit about 25. But yeah, that last example we did the very last time we did that on Tuesday. Those out there, I'm gonna have to, at least for the moment, suspend that for a viewing audience. Just wanted to talk about the conditions for electrostatic equilibrium and move on for now. Or should I? Maybe I should end with that because then 25, yeah. We're gonna do 25 today anyway. Okay. So yeah, I'm gonna talk about that last example. '24. So we have a sphere inside a spherical shell. A solid insulating sphere, radius A, carries a net positive charge Q uniformly distributed throughout its volume. A conducting spherical shell of inner radius B and outer radius C is concentric with the solid shell and carries a net charge negative 2Q. Using Gauss's law, find the electric field at various points and the charge distribution on the shell when the entire system is in electrostatic equilibrium. So we have a picture that looks like this. We have this sphere inside this spherical shell. It has radius A. It has charge Q. And we kind of color it in. And then we have this Gaussian surface right outside of it. And that surface has radius R. It's making different colors, I guess. Radius R. And then then it's a spherical shell. Oops. And we have the inner lining of that spherical shell, the cross-sectional area. This is negative 2Q. This will be radius C, going all the way to the extent of the shell. And then this will be radius B at the inner part of the shell. So B, C, and R. And again, this is Q. And so for the different conditions, okay, at point 1, on the interior, we want to find the electric field inside of the charge. Then 2, we want to find the electric field at this Gaussian surface. Then 3, we want to find it on the interior of this shell. And 4, someplace out there. Well, without too much ado, we found 1 already in the previous example on the interior. So we can go ahead and say that the electric field, write this in black. The electric field at 1 is going to be, if you remember, it's KQ over AQ times R. And we go back there just a little bit. So this is what we found for the interior. And linear with respect to R, right? So that's on the inside, and that the outside, that's easy, right? We have this Gaussian surface here, so it's enclosing all of it. So the electric field at that point is like your regular old electric field equation, KQ over R squared. You know, not to confuse, it's little r, same thing. And then at 3, it's kind of, we have to be, a little careful about that. At that point, a couple of approaches. Based on the conditions of electrostatic equilibrium, all the charge resides on the surface. There is no charge on this interior. Hence, no electric field at 3. Just right at that point. Also, 2, there is no defined radius at that interior point. That may be a little bit arbitrary to think about, but there's no defined R, like radius D at that point. But also, too, there's just nothing, there's no charge at that point. There's a charge on the interior, it's a DQ, it goes all the way to A. There's a charge enclosed here, but when we go here, at this point, there's nothing. So E3 is 0. And then E4, we're enclosing this entire thing. So we're looking at every possible charge in the book. We don't even care about the fact that there's nothing here. We're going to look at 2Q and Q. We're looking at the whole, shebang, because this is enclosing the entire picture. So as we do that, the charge is going to be a sum of negative 2Q plus Q, or K, and outside there, over, call it R squared, you can call it C squared or whatever, but just radius R. And that's going to be negative K Q over R squared. And so those are our different ways that we can look at this conductor in electrostatic equilibrium. We're using a little principle. This one's probably the trickiest. See that there's nothing here, no charge at that point. And then the other places, electric field, sum of these negative 2Q and Q on the very outside. And then right here, we're enclosing Q. And then on the interior, we found that earlier, which is that. So different charge configurations, like in this case, it's spheres. You can do a line, you can do a sheet of paper, or just a sheet of charge to figure out your different electric fields. And so that That was last example, chapter 24. So good, we made good on that review. Again, we'll come back to problem solving more as we get to 25. And we'll backtrack a little bit. So I want to introduce a little bit in the small time we have left in 25. You know, let's talk about the concept of electric potential. Electric potential is basically, I like to think of it as the ability to set up an electric field. It's the possibility, potential for an electric field. That's in turn going to help us look at voltage difference in electric potential. After voltage, you look into current. The current, look at resistance, Ohm's law. Then we're talking about dynamic charges or charges in motion, changing electric fields, currents, producing magnetic fields. And we start getting to the heavy lifting. So, good times. So chapter 25, I just want to define some terms. So first section is electric potential and potential difference. All right. Back in the day, we have defined potential energy, it's gravitational potential energy, as the integral or the negative change of work. Work is the negative change of potential. Potential is a negative change of, not the negative change of work is equal to negative work. The potential change in the potential energy change is equal to negative work. So we have these terms, F, say on x-axis, dealing with this mass on the spring, a horizontal mass spring system. This would be finding potential energy. And I like to think of it more commonly with gravitational potential, because the work of a spring is going to be 1/2 kx squared, but you can do negative 1/2 kx squared. But it's a little bit troublesome to think about it only in that sense. So I like to, even though I wrote this as x, I like to think of it in terms of y, which is a gravitational force. Why do I like to think about it like that? Because if I'm going to raise an object into the air, I'm increasing its potential energy. I'm giving it a positive delta U. And that's going to be equal and opposite this work. Or better yet, it's going to be opposite the amount of work that's done by gravity. Gravity is pointing down and the displacement is up. So the work done by gravity will be negative. That's why I got this here in terms of the y-axis. But I've increased my potential. Okay, so, but that's the basic definition. So vice versa, I could have, something like this. Negative delta U equals the integral of, where Fx is the force in the x direction. It's the same thing. If I do positive work here, I am losing potential. If I do negative work here, I'm gaining potential. This is an object being raised into the air. This is the object being dropped. Now, in terms of, we're going to go from gravity. In terms of the electric field, works very similar. Works, basically the same. So when we have an object falling, it's falling in the midst of a gravitational field. And we have a charge falling from positive potential to a negative potential. So it's the same kind of physics. So we have a positive. Positive don't like that. So I'm going to come down like this through this electric field. So they go to the negative region. So the work done by this electric field, the work done by it is going to be equal to the negative change in potential. I'm losing potential here. This will be high potential or positive potential. This is the maximum, and this is low or ground, as we were going to get used to seeing as we go along. So this is high potential, this is low potential, this is ground. I'm coming down to the ground state or ground area or zero. This is like the ground. And when we're dropping an object from high potential in the air through a gravitational field, it's the same thing. But it's not just talking about charges. And so the vice versa, we can go back, but we have to put some work in the system to get a positive charge to go from what it likes back up here. So we have to put some energy in there. But we'll get to that. So the basic definition, I'm rising, I'm being lifted in the air, and I'm falling. So going further, in terms of gaining potential in an electric field, I changed my force, expression to the electric force. So so electric force. Now I'm just going to say arbitrary points A and B. This is start and this is finish. Well, electric force is going to be E times Q. I'll say test charge Q naught. And let's say some arbitrary distance, not just X, Y, Z, just call it some line, call it S or R, whatever, you know. We know that this is going to be a line. It's going to go from one point to the next, initial to final, final minus initial, displacement. It's a line integral. Why do we get this? Because we know that electric field is force over Q naught, and force is E times Q naught, or Q naught times E. It's this. So I go one step further, and my delta U will be equal to negative Q integral E dot ds from A to B. So I'm going to be integrating from A to B. This comes out to B. So this E is going to come out of integral. We know that. But in this form, as we know, these are just positions. A and B are positions. So again, as we also know, this does not depend on the path. If the particle for some reason was going at an angle, and it, you know, if the electric field was not uniform, it was off axis or something, as long as it reached from A to B, it doesn't matter the path. So it does not depend on path. It's a line, and the path could be some squirrely thing, linear. Well, we have this here, and this is test charge. We define, or we divide delta U by the test charge. We get something known as a potential difference, electric potential difference, or a voltage. But I'm going to get to the voltage later. Instead of having a difference, it's U over Q naught. This would be my electric potential. And this is my definition of electric potential, is basically potential energy divided by charge. Energy per charge is electric potential. This value depends on the source charge distribution, if it's positive, negative. So this potential is going to be this quantity, but it's going to be uniform throughout this entire region for electric potential. Now, in terms of what we have, and I'll let you guys go here. what we have, and for delta U, because it's delta, we make this delta V equals delta U, which is delta U, there you have it, because this is definition, so we're not dealing with just static. This is going to be like the potential at any point. Say the other thing I just said about potential at any point. This is going to be the difference between 2 points, my potential difference, aka my voltage. Right? It's a basic definition. So we have, again, integral a to b, e dot ds, where ds is going to be integrated between those 2 points. This right here is the potential difference equation, aka voltage. If I have a difference in potential, I can send a charge through. If the boundaries were the same potential, nothing happens. And we'll start talking along and talking about current, which is the rate of change of the charge, or how these charges move in time. Current, charge over time. Rate of change of those movements of charge, yeah. Current. For voltage is just, okay, I'm just static. Voltage is not same as current, even though it got charges moving. So the charges are going to be the current. You know, when we're looking at moving charge, we're looking at the current. Voltage is just, okay, I got 2 regions. Let's say that they're different they're different regions, positive and negative. I have the ability to send a charge through. That is my potential energy difference. But nothing's happening necessarily yet, but I can have it. So that's where I want to stop. Thank you guys for being good audience. Stop right there.